and I would like to welcome you to this lightning session of the topic Atmospheric and Subsurface Radionuclide Background and Dispersion. We are excited to have about 50 presentations. I want to just tell the speakers that they have 1 minute for their presentation, so let's please keep it short and precise, and I wish you good luck. And my colleague?
Also a very warm welcome from my side. So I'm working for the Austrian National Agency for Geophysics, Geology, Meteorology and Climatology. And my focus is on ATM, but thanks to CTBT in the past years, I also gained some knowledge about the interpretation of radionuclide measurements. Yeah, just to add, you will find a list of the presenters and the proper order in which to queue, and you will also find information on the touch screen where you are supposed to go to after this lightning talk. Okay, with this, I wish ourselves a nice hour, and I give the floor to the presenters.
Yes, good morning. I'm Doris Say from United Republic of Tanzania. My presentation is about testing the hypothesis that light water reactor is likely being the source of xenon-135, which has been detected in most IMS noble gas stations. So we did backward simulations for 24 to 72 hours for stations which detected this radioxenon. So we started with multiple stations, and these are USA, Norway, and Sweden. Again, we did the same thing for the station which simultaneously detected xenon-135, and this is Sweden. So we have very nice presentation. Please join us to our poster, board number 4. Thank you.
Good morning. My name is So, and I'm working at Korea Atomic Energy Research Institute. Atmospheric dispersion and those assessment models have been applied to evaluate the behavior of the radionuclides released into the air for a hypothetical nuclear accident at Zaporizhzhia site. The two models are key component of radiological accident preparedness system in Korea developed by Korea Atomic Energy Research Institute. The simulated result shows radioactive plumes initially moved to the eastern part of Europe, and later they transported to Asia and North America regions due to the westerly wind. The simulated effective dose rate shows over 1 millisievert near the Zaporizhzhia site, and it was below 0.1 millisievert in the rest of the Europe and Asia and North America. That's it. Thank you.
Hello. So my name's George Nurser. I'm from the National Oceanography Centre in Southampton in the UK. And we've been doing something very simple in that we've been inserting tracers which represent radionuclide poisoned waters in the ocean, and we've been seeing how variable is the amount of dilution and the spread of the contaminated waters. And not surprisingly, as you can see from the figure, indeed the dilution does very strongly, in fact up to a factor of about 100 after 3 or 4 months. Thank you.
Good morning. My name is Celia. My poster is about the influence of the routine discharge of the nuclear power plant located in the Florida Peninsula. During the influence in this area are a geographical area of the migratory anticyclone. The main result of this study is about the air massive transit over the northern of the Caribbean Sea during the influence of the migratory anticyclone, while the center of the anticyclone was located in the center of North America, and the center was located on the state of the Texas.
Good morning, I'm your boy Eugenia, and I will be presenting on the determination of radon concentration, the determination of turbulent diffusion coefficient using radon concentration. And also we would compare turbulence parameters and also metrological parameters with radon concentration as well as turbulent diffusion coefficient, and also the effects of turbulent diffusion coefficient on radon concentration, as well as considering radon concentration measurement from two different areas, which is the canyon and also the open area. So if you are interested, you are welcome to our poster. Thank you very much.
Hello, I am Pierre Adler. So if you are interested by a rapid estimation of gas and tracer outputs from a cavity after a nuclear explosion, then come to see my poster. So we work on this configuration here, where we solve the Darcy equations, of course, with transfers between the various units, and the transport equation as well. A typical result would be this one on the right, with the mass of tracer which goes out as a function of time. So thank you.
Hi everybody, I'm Eric Pully from the French Atomic Energy Commission, and my work deals with a ground truth experiment for the atmospheric detectability of xenon emitted from an underground cavity. I welcome you to the very unique Roseland Natural Laboratory, which is located in the French Alps. Come to see my poster if you want to find more about how we injected into an underground cavity stable xenon and SF6 as surrogate tracers of gases that could be emitted to the atmosphere following an underground nuclear explosions. Also, how we monitor the breakthrough of these tracers in the subsurface and in the atmosphere, and why. The little spoil that we are interested in understanding the coupling between the geosphere and the atmosphere. Hi again. This time, my other works with the PhD students deals with coupling condensation with decay chains. We develop a refined model for the calculation of the radioxenon source term produced by underground nuclear explosions. The radioxenon precursors are moderately volatile elements that condense within the magma of the nuclear cavity when the system cools down. So come to see my poster again to find out more about our refined model, and which takes into account condensation and evaporations, and then you will discover why magma does matter. The little spoil is that this changes the quantity of radioxenon emitted to the atmosphere, as well as its isotopic ratios. Thank you.
Yeah, good morning. So I think, as we all know, there are challenges. Back. What? Oh, I don't. Okay. So, yeah, as you all know, there are challenges regarding detecting underground nuclear explosions, and we are testing a new approach, and this implies combining data assimilation called nudging. So this is our specific approach together with machine learning for anomaly detection. And first results demonstrate an ability of this assimilation, of this data assimilation approach, but also highlights some challenges we are facing. And finally, we present two different venting scenarios for which we think that these new methods can be exploited. Thank you.
Good morning. Our poster nicely follows the previous poster in the sense that it is a companion project poster about xenon background estimation. We like to clarify nudging a bit more because nudging is a nice method to calibrate ATM predictions based on emissions, unknown emissions by known sources, to make these predictions more IMS sensitive so that we can compare them downstream with more confidence to other IMS measurements. So please nudge yourself to our posters. We are neighboring posters, and I can already tell you that there's another nudging poster, so we have maximum exposure here, so a lot of exposure here for nudging. Thank you very much.
Hello, I'm Michael Fox from Pacific Northwest National Lab. I have a poster on a large physics experiment that we had in Nevada Nuclear Security Site, or National Security Site, and with that we had about 16.3 tons of Comp B that we detonated to monitor what were the seismic signals, a large kind of infrasound signal, what happened with the gas migration. So a large portion of this looks at tunnel gases, subsurface gas transport, and understanding what do those do in the presence of a large pressure source. If you come to the poster, I'll give you the overview of what we did from end to end in terms of setup all the way through execution and our plans down the road. And then there's a handful of other posters and presentations as well that will dive into some of the specific details of the experiment. Thank you.
Good morning, everyone. My name is Sepide. Our poster is about a statistical analysis of nuclear power plant outages as sources of elevated radio xenon. This is important for CTBT verification because the xenon detected by IMS network often comes from the reactor shutdowns and restarts. We analyzed outage, duration, and also frequency across different reactor types and different causes. We found that refueling with maintenance, cause C, lead to the longest and the most frequent outages, which are linked to prolonged radio xenon emissions, while shorter outages cause brief spikes. Please stop by our poster. I will be happy to discuss our results in more detail.
So, hello everyone. I'm Léo Adoni. I'm working with École Normale Supérieure in Paris. I will present to you a new toolkit to model radioactive atmospheric pollution transport over all the hemisphere. It's called Karateka, and if you want to know more about Shimmer and Karateka, please visit at board 21. Thank you.
I'm back with one of those posters I mentioned of looking into some of the details for the experiment. This one is looking at variability for xenon and tritium transport through the subsurface. Those were two tracers that we put into the experiment to see how they transported through the subsurface and into the tunnel. This was driven mostly by, you can see on the left-hand side, some real-time xenon sensor measurements to understand minute by minute where the xenon is and how it's transporting, along with some laboratory measurements that we have in the middle picture and the right-hand picture, looking at gas collections that we perform to collect the tritium and then process that and measure that in the laboratory back at Pacific Northwest National Lab. And understanding the transport variability is important to see what the difference is between xenon and tritium, as there's a lot of geologic media parameters, gas sizes, gas chemistry that comes into play when we start to look for the transport of those two species. And here you'll see kind of there's a large team that's involved with this, along with the experiment execution. I can't list them all, but there's a lot of folks that are involved in this effort. Thank you.
Good morning, I'm Johannes Fleisch from the University of Vienna. As already announced, I'm the other poster about nudging, where we try to improve the global background concentration fields of xenon-133 by applying nudging in FlexProt LCM for 2014. One main research objective has been to successfully implement nudging in FlexProt LCM, but also to conduct sensitivity experiments by altering the spatial kernel widths and assessing the performance of nudging at assimilation but also at validation stations. There have been incredible improvements at assimilation stations, but there are still challenges for the validation stations. So if you want to chat about that and how we can move forward together, come to my poster and we can talk about that. Thank you.
Good morning. There is a presentation here, but I'm going to talk about the background of xenon 133 in both hemispheres and the comparison between them and how is the trend in each hemisphere of the background of xenon 133. And it's all. Thank you.
Good morning. My name is Said Khima from Egyptian National Data Center. I'm specialized in atmospheric transport modeling. This poster talks about some suggestion to improve the source estimation in WebGrip. This is one example how we can confine the source area. In the poster, we discuss some criteria should be considered when we make source estimation regarding timing of concentration, regarding some statistical criteria should be considered in the concentration itself. Thank you so much.
Hello, good morning everyone. My name is Mohammed Ahmed Mohammed Zain and I'm a station operator of IMS RN43 in Nouakchott, Mauritania. Our poster presents the first result on air quality monitoring at RN43. In Nouakchott, Mauritania, Saharan dust storms are part of daily life, and PM10 level often exceed WHO and EU limit. Every day we monitor PM10 with the Snow White air sampler integrated to our station, and we compare and using the gravimetric method, and we compare the result with the radionuclides such as beryllium-7, potassium-40, and Pb-210. Thank you.
Yes. Good morning. My name is Vitus Abel Barabegwa from Tanzania Atomic Energy Commission. So my e-poster will be on a review of data from LIN 604 station located in Dar es Salaam. So I have some recommendations. And, the interest was on the anthropological radionuclide detected on the station. This activation, the efficient product detected from the past 10 years ago. Thank you.
Hi. Okay, so in this work about pollution source detection, we used a standard approach for pollution identification, backward simulations from individual sensors. This is the standard approach, but in our work, we demonstrated that if we aggregate results of these backward simulations from individual sensors using a Bayesian model, we can identify the source of pollution significantly better. So we made experiments both on open source data sets and on Fukushima data set from CTBTO. Thank you.
Good morning, everybody. It's great to see so many people up about, here. It's a beautiful day, it's a beautiful city. I'm glad you're here listening to us. I'm Matthias Aldener. I'm from the Swedish Defense Research Agency, FOI. And this poster will be about something we've done for the last decade, measuring natural background of xenon in the soil. And this is important for OSI to know, what can you expect even if there's no nuclear weapons. So this is something we've done over the years in Sweden. And I will not tell you anything about it, but if you come, there are a lot of data, there are a lot of vivid discussions. There are 3 people over there that were in the field, so they can happily, we're plenty of people, so you can come, a lot of you, we'll be at position 37. And I'll tell you the most interesting part. We did not only measure xenon 133, we actually optimized and measured xenon 135 naturally in the ground. So if you want to know more about it, ratios, come see us. I'm happy to discuss this as long as you want. Thank you.
Good morning, I'm Ole Ross from the German NDC. Together with my colleagues Sophia Rander from the BFS and Patrick Hooper from the BGR, we are showing results of atmospheric transport modeling for the Japanese station RN38. It has a particular interesting history of detecting as well background sources as well as radioxenon, which could be attributed to North Korean test explosions. In the last 2 years, there was an increase of frequency and height of radioxenon levels, and we performed backward modeling for the 115 highest xenon concentrations there with a GFS 0.25 metrology, and looked where they coincide, just stacked the results, and the message is whenever there was xenon in the air, between 1 and 4 days transport time, those sensitivities coincide in the Yongbyon area and not at the test site. So there is an overwhelming majority of air coming from there if xenon is in it. Thank you.
I am Michiel de Bode from the National Institute for Public Health and Environment of the Netherlands, and I'm going to present at the poster something about a new method we developed with which we can calculate the progeny of any given source term very fast, and we go from 1 minute to 2 million years within seconds. We have the whole calculation done. And then we apply this to a case for xenon ratios of nuclear detonations. I hope to see you at my poster for a nice discussion. Thank you. Now for something completely different. I'm having another poster about the backward ATM calculations. With the exercise of the MPE 2024, the Netherlands, Luxembourg and Belgium worked together, and we did comparisons of both our models from the Belgium and the Netherlands, how they compare and what we can learn from it. I hope to see you at this poster as well.
Good morning, it's great to be here in Vienna. My name's Susan and I work at AWE in the UK. And today I'm going to be presenting a poster about uncertainties in atmospheric transport modelling. So when we're trying to model the background of xenon, it's really important to understand the uncertainties in how the atmosphere has transported that xenon. So we've done this in the context of the Xena project. So that was xenon at Hartlepool using some cubes in the northeast of England and looking at transport from IRE. And we've explored this using 2 atmospheric transport models a variety of meteorological data and also varying elements of the source. Thank you. Hi, my name is Sophia Brander. I work at BFS, that's the Federal Radiation Protection Agency in Germany. And BFS is a name that pops up sometimes in the field of xenon measurements, and that's because we have this really long tradition of measuring xenon in Germany, so we have almost 50 years of measurement data, but it's weekly measurements, and now there's the Sonar cubes coming up, so we also have 2 cubes now, and this poster is about what's happening, like we're changing things in our network, where are we going to put the cubes. On this picture on the right-hand side, you can see forwards modeling from IAE Fleurus. This was done by Ole Ross, my colleague from BGR, and it just shows the background that we're expecting around Europe, and this also plays a role when we think about where to put the next cube. So I'll be happy to see you at my poster. Thanks.
Good morning again. My poster is about the possible source origin of the detection of the cesium 137 in the station located in Mexico, MXP 44. The back trajectory were simulated with the high-split trajectory model, and the main result of this study is the possible origin, source origin, where was the episodic emission of the Diablo Canyon nuclear power plant. Thank you.
Hi, this is not my poster. I'm Carrie Seifert from Pacific Northwest National Laboratory. The poster I'm going to present today is on a toy model that we built to understand under what conditions subsurface transport models are relevant to downwind detections. So we're trying to understand if you assume that you need a minimum detectable concentration at a reasonable location downwind from a reasonable station, what does that imply about your subsurface conditions that are required in order to achieve that concentration? So come see me, poster number 54, just right inside the door. Thanks.
Hi, good morning, everybody. My name is Mufrah Al-Rashidi. I'm from Kuwait Institute for Scientific Research. We're going to present in this poster the collected data for the last 10 years and try to figure out one scientific questions: why the high detection frequency of the cesium occurred in RM40 station, and what is the reason behind that one. Also, we collect the temporal analysis for the dust event and the dust blowing from the meteorological point of view, and compare this dust event with the high detection of the cesium and see the effect and the source of the cesium which is detected at the RM40 stations. And the poster is in booth 55. You are welcome to come pass by to see the data and the analysis. Thank you.
Determination of turbulent diffusion coefficient using atmospheric radon concentration. The role of turbulent diffusion coefficient in the dispersion of radon concentration in the atmosphere. The measurement of radon concentration in 2 different environments, which is a canyon and a flat surface, under 3 different stratifications, as well as how turbulent and meteorological parameters affect the distribution of radon concentration in the atmosphere. You are welcome to our stand if you would like to learn more.
applications in nuclear explosion monitoring is the prediction of concentrations at IMS global gas systems. This poster is about the use of predictive source models created from STUX data. This is source term analysis of Xenon project data from the PNL and others project. You see the long list of authors that are all behind this project. We simulate the IMS concentrations at various stations with 3 different source models. Of course, as a baseline, we use constant source assumptions from the literature. Second source model is distribution of STUX data over long time. And the third model is STUX data with high time resolution. So what do you think, which of these models win the competition? Be ready for surprise. And what happens if there are 2 STUX data at 2 different facilities for the same stations?
Hello, on behalf of Radiation Protection Center in Lithuania, I'm happy to announce that network of 3,000 cubes and 1,003 devices have been deployed in Lithuania, and now it's fully functioning. We are receiving good quality data on radioxenon measurements in atmosphere and trying to trace possible sources of releases. For that, we are using high-split backward trajectory and dispersion atmospheric transport modeling. But implementation of the PSR and FREER method for source attribution analysis is currently in progress. Thank you very much.
Hi everyone. I'm just waiting for my slide because it's not this one. Yes, it's this one. So hi everyone, I'm Mounir Atik from the CA in France, and I work on atmospheric radioxenon monitoring. And this poster is about characterization of the civil background based on simulated data. And the particularity of this simulation is they are organized by source, regional nuclear plant by areas, or medical isotope production factories, which allow us to know the contribution of each source in the total concentration measured at each station. And this particularity allows us to build graph models assessing similarity between source mixture measured at each station. And based on these graph models, we perform clustering and source separation from the aggregated concentration. And we have hope that this source separation can allow us to perform more refined anomaly detection method. Thank you.
Good morning. Good morning, everyone. My name is Hajar Hamrashdi. I'm presenting my team from Sultan Qaboos University, who is working on developing the benchmarking norm map of Oman. Our poster is about mapping norm and background radiation across the whole country. And in our poster, you are going to see why mapping norm and background radiation is important at this time in history. What we did so far is creating a grid map, and we started also collecting and preparing the samples, and we managed to also get few results as well. The most important result of our work is creating a baseline for background radiation in the Sultanate, and please come and visit us in booth number 1 to find out more about our work that we are conducting in this study. Thank you very much.